Hello.
Yeah.
Where is the keyboard?
So was anybody running that whiteboard?
Oh. Where is it already running? Oh. Nice. Thank you. How was the exam? Did okay? No? Bad? Give me some feedback. How was the exam? Good? Who went below what they should be? Who went below what they thought they should be? Uh-oh. Really? Then why you say it's okay? What's the issue? Could not read the question, lack of time, still don't know how to see the table. What are the issues? There's got to be something. Some of final values went. Final answers. Okay, I don't see anything with it. 7 and 7.12. I don't think you're going to lose marks for that. No, but you cannot use slightly different. You must have rounded off. But then it has to be the table value. From where else will you get a value? Huh? You have to write it off of the table only, right? The only difference between what you write and the table is you might round it off. So when you round it off, the final answer a little bit goes of. Yeah, procedure is correct. Final answer is wrong. Usually won't happen. Because the whole point in saying the procedure is correct means you have taken the right values out of the table. Correct? That is what procedure is correct means. So what could happen with the wrong answer is straight up your calculation is wrong. In a hurry you must have. Then that part I get it. I don't think by writing a wrong number, I don't think anybody will write a wrong number and call the procedure to be correct. Is that possible? No, it's not possible. So anyway, I don't know what the average is, or I don't care what the average is and things like that. Well, the exam was set for how much? 9-0. I think as long as you understand concepts here, around 50, 60, I think it's good. Doesn't mean that anything higher is bad either. So you are still in chapter 6 if I understand correct with your tutorial. Am I right? You got to move it. You got to move fast a little more. You missed one today now. So you're losing a lot of tutorials. Okay, I have some fun things. So go back to heat engine. One more time, write the diagram. I'll also write with you. So I'm not going to write all the appliances. I'm just going to write where you have the boiler, where you're going to get the heat. You're going to get the heat, and then when you get heat, what will you do? Work. And then you will also discard. Yes, this is what we did last time. So you're going to discard some heat. It's going to be a waste. There's always going to be a waste. That's the whole statement of Kelvin, that entire heat that is supplied cannot be converted into work. So can you write a schematic without putting the compressor? Write it. Just the boiler, the evaporator, or the heater, or the boiler, whatever you want to call it. So boil, what should I do? Apply heat. The only difference between this chapter and the other chapter for all the Q's and just for the Q's, I will have to identify by H and L. Hot location, hot junction and cold junction. So I am supplying heat at what junction? Hot junction. And then what do you get? Some work. And then you are going to discard some heat. Can you write it? Cold location. I wrote L, low temperature location. Cold junction, cold location. So hot location to cold location. This is your heat engine. If you give heat transfer, you will get work transfer. If you give work transfer, you will get heat transfer. Yes? You cannot have one without the other. You cannot have one without the other. It is interdependent. That's the take home for today. That Q and W is interdependent. So eventually you contemplate on Kelvin statement and Flashier statement. That's basically the conclusion that you will get. Got it? That you need one for the other. So in this case, you need Q for W. You want work from your machine. What's the efficiency of the machine? Output by input. What's your input? You are supplying heat, not work. You're supplying heat. What's your output that you're getting? Work. So that depends how well you studied, depending on how much digression you do, how much heat is discarded. So W is equal to how much? QH minus QL. Which is the entire heat that's supplied. If it completely gets converted to work, what equation will you write? QH is equal to, if the entire heat that is supplied is converted to work, what will you write? But that doesn't happen. What happens is you get some work and then you get, what should I write? QL. So for this case you write the diagram. Right now, convert this to write a diagram where that entire heat is converted to work. Write the diagram. Which Kelvin statement says it's an impossibility. It is an impossibility. You need to have heat being dispersed or discarded or dumped in the low temperature location, because the entropy of the surroundings has to increase. Otherwise, the process will not happen. That's the whole point. If it finally goes down to entropy, you need to have energy being discarded somewhere where either the entropy of the surroundings will increase or the entropy of the system should increase, so that there is a net overall change in entropy of the universe. Or it can be the same. It cannot decrease. Entropy cannot decrease. Write down for Kelvin. Write the picture. Write the schematic. QH is equal to W. There is no heat being discarded in the lower junction, low temperature junction. So nothing. You put a boiler, you put QH, and that simply goes to work. There's nothing coming out. So this is impossible. Okay, QH equals W. Not going to happen. So what did you write your efficiency as? You have supplied heat and you got work. How do you get maximum efficiency? If the rejection is less. Lower the rejection, you will get a lot of work. Not going to happen. So what you should do here is to identify where the entropy is increasing. Entropy is increasing from the heat that is being discarded. First, the entropy is increasing in your material because heat is being supplied from outside, correct? By boiling. So there the entropy of your material is increasing. But then what you do with that entropy? You end up orienting it and use it for work. So the entropy actually sort of temporarily goes down, but that is not going to be a spontaneous process. That's not a spontaneous process. So then the heat has to get discarded somewhere so that the entropy again of the outside should increase. So the net entropy should increase. That's where the entropy comes in, through this heat engine example. Okay, now let's go to the next appliance, refrigeration. What's the deal with the refrigeration? Just tell me what is a small, so what is a, if I ask you for 2 marks, so what is the application of heat engine? There's 2 marks. You have to write it in a single phrase. What will you write? What is the purpose of a heat engine? What will you write? It is an appliance wherein, fill in the blank. Louder. Where I can generate work by using heat. That's it.
There's nothing complicated about it. Where I can try to generate work by using heat.
You see, you use both the words in the same sentence, so they're interdependent.
Got it? So that's why you have to learn how to frame the sentence. Where I can generate work by using. Immediately you have to say by using. It's interdependent. Now, why do you need a refrigerator?
So again, see if both heat and work will be there in your sentence. It's a device wherein you have to do work to remove heat from a so-called refrigerated space.
Very good. That's it. That's a simple definition. You have to do work.
So what is the Cauchy statement?
That without doing work, you cannot do that. You cannot simply sit and do miracle prayer in front of the refrigerator and say, you suck the heat out from the refrigerated space. That will not happen. It will happen only if you do work. In the first case, you need heat to do work. In the second case, you need to do work to remove heat. Because this is not a natural dispersion. Because in the refrigerated space, you are not removing heat from, you are not transferring heat from hot to cold. What are you doing? Are you transferring heat from hot to cold? Are you making the hot region colder? Yeah, you're making the hot region colder. So which is spontaneous? To make the cold region hot or the hot region cold? How? It will always flow from hot to cold. So usually the cold region will always get hotter. But here what are you doing? You're taking a region and making it much more colder. And you're transferring that heat from that place. It's not a natural process. It's not a natural process. Yes? So you go to a new page. So you already have a refrigerated space which has T1. You take it to T2. So what are you doing? What is your gradient? Is this positive or negative? Huh? Negative. Will it work spontaneously? It won't work spontaneously. Write it however you want. In the heating case, what happens? Your temperature is initially T1 and then it will become T2. What is the gradient rate? T2 minus T1. That will work. Removing heat is not a natural process. So how to make this happen, guys? How to make this happen? Any of you have heard of something called as phase change materials? Phase change materials. So refrigerants are phase change materials, are they? Do they go from liquid to vapor, vapor to liquid? Is there a vapor-liquid transition that's happening in the refrigerant or no? Yes, but today there is a new section of materials they call as phase change materials just because the transition is from solid to liquid and reverse. Instead of liquid to vapor, you have solid to liquid. So previously also refrigerant materials are also phase change materials. But you just have a new term these days, phase change materials, because the transition is from solid to liquid, not from liquid to vapor and vapor to liquid. Solid to liquid, liquid to solid. The cycle keeps going. Any idea why that came about? Because you see, you want to store food, you can use a refrigerator. Where the phase transition will happen mostly at what temperature? The refrigerant liquid becoming vapor, typically in your refrigerator, at what temperature it might happen? Will it happen at 4 degrees? Will it happen at 24 degrees? What temperature do you think this transition is happening? A refrigerator is not just cooling, but it's also maintaining the temperature, correct? So what temperature is it maintaining? Usually a refrigerator, not the freezer, just your regular refrigerator space, where you keep your vegetables, not your ice cream. Around what temperature? Is there ice being formed? No. So typically, will it be higher than 0? Yeah, refrigerators temperatures are, unless you have put the cooler setting to very high level, it will be about 3 degrees, 4 degrees. The freezer, -8, -9, -12, freezer. So, in the refrigerator, if it's 4 degrees, it's being maintained. Your vegetables are safe at 4 degrees. This transition of vapor to liquid and liquid to vapor should be happening at what temperature? See, if you didn't have this transition, in the refrigerated space there is 4 degrees. Your room temperature is about 30 degrees. No matter what your insulation, what will happen inside your refrigerator, 4 might become 7. It will get heated up, right? Your outside is hotter. Yes? Your outside temperature is hot. How the 4 degrees is maintained inside? How is it maintained? There has to be a heat sink, which is removing the heat and maintaining the temperature at 4 degrees. Yes? Otherwise, 4 will shoot up to 7, then shoot up to 8, and then it might even go to 15, and your vegetables will get spoiled. All of you know when the power gets shut off, what happens? The refrigerator space gets heated up, or does it remain 4 degrees? It got heated up. So when it's on, how is it being maintained? Somebody is taking the heat out, correct? Yes? Who is taking the heat out? The refrigerant. How? Excellent. That is the heat sink. The liquid refrigerant is being converted to vapor. Is it endothermic or exothermic? Endothermic. Heat sink means you have to draw the heat from one place and dump it in another place. How do you dump it? Either you can suck the heat out, or you have to phase transition and take all the heat and become something else. So in this case, what happens? The liquid will become vapor. So at what temperature this could be happening for you to maintain 4 degrees? Around 4 degrees or far away from 4 degrees? Around. Obviously around 4 degrees. Got it? Yes? So if this was all very good with the refrigerant, why phase change materials where the same concept of solid to liquid transition came about today, in today's world? Okay, but in the refrigerator, you're not moving your refrigerator anywhere, you keep it in the kitchen in one place. You actually brought up a very good point. That's one of the main reasons why solid to liquid transition came about. Because today, what is the requirement of having freezers? Is it just a stationary freezer that you're requiring, or a stationary refrigerator, or today we require mobile mobile, we require mobile refrigerators. We require portable refrigerators and mobile refrigerators. Where? Give me one example. What if you ordered something, right? Some truck keeps coming to your campus. What truck? Who is your big online grocery guy? Louder! So he does bring a lot of items that are supposed to be kept at 4 degrees, yes? How does he bring it in the truck? Just putting ice will not work like old times. What will happen? That is not efficient. What will happen to the ice? It's all messy. It will become water and all messy. So these days they are packing with solid phase change materials, which will actually melt at around 4 degrees and 5 degrees. So there's a company in India which supplies these phase change materials. So they put it in capsules or in button forms or like in styrofoam package. And these guys just load it up around their product, and then they hope that it will phase transition and keep the temperature same, that the food will not get heated up. So just like a refrigeration, they will pack their contents with these phase change materials around it. So I asked them, how do you even pack? They said nothing very scientific. We take bottles. So we fill these bottles with these phase change materials and just pack the bottles around like really well in the container. Just with regular bottles. But bottles of different designs, so that the packing is very good. Got it? So you have surrounded your material by a solid refrigerant. For the lack of better word, I have to use a solid refrigerant. So it's not really a classic refrigerator, but you are using solid refrigerant. In that case, the phase transition is from solid to liquid. In what you mentioned, the phase transition is from liquid to vapor. What is the other thing that phase change materials is good, which refrigerants do not do the job? First thing, its vapors will be there. It might leak out. There might be losses. But the most important thing is the environment. All of you know about refrigerants. They damage this. Whatever in the tables you guys look, right? R. All those R's are very harmful for ozone. They're depleting the ozone layer. They give out freons, huh? Yeah. So refrigerants destroy your ozone. They're not good chemicals. When they come out as vapor, when they leak out as vapor, they go and attack the ozone layer. I think this is an old story. Heard about it? So that is why we are slowly moving into solid liquid transition. And we have just given a name as phase change material. It's nothing but a solid refrigerant. So I already said it's a solid refrigerant. So where is the work being done? Because that solid will become a liquid and take the heat out. But for that you first had to have a solid. So did you put your work to make that into a solid? That is the work. Because if there was no solid, and if that solid did not melt at 4 degrees, then you do not have a heat sink. So now go back to your refrigerant also. If the refrigerant was not a liquid, but instead a vapor, would you have a heat sink? No. So how do you convert that liquid, that vapor into a liquid? You have to compress it. You have to do work. So that is where the work. Now can you write the schematic? You have to do work. Very good. So how do I write here? So you are removing heat from the cold junction. Correct? You are removing heat from the cold junction. This is a refrigerated space. This is a refrigerated space. So you said it is endothermic, correct? It's a heat sink. It's endothermic. So endothermic means liquid is becoming vapor. So what kind of a gadget? Sort of like an evaporator, correct? Evaporators
So what happened in the evaporated liquid became vapor. Now this vapor is coming here. But for you to get it back into a liquid form again, this vapor has to be compressed. Compress it. So when you compress, what happens? Work is being done on the material and the pressure increases. So it condenses. So then it comes to the condenser, and what will it become? What will it become? Liquid back again, vapor to liquid. Is there a rejection of heat? Yes. And it's hot. QH. QH. And now that liquid will come, go through a valve, put one valve this, and back again into the evaporator. You got your cycle. So I will write QH. Okay. Here I have to put an arrow and say W. Did I put correctly? W. Because if you don't have work here, if you don't compress, what will happen? QL will simply be QL. Simply that heat will go there. Got it? Just the heat will get transferred there, that's all. One more time. More than that, firstly, that is the most important property, right? The endothermic of melting should be compared with the endothermic enthalpy of vaporization. But usually, which one will be higher intuitively? Delta H melting will always be lower than delta H vaporization. If you go look for any material, VAP is always higher than melt. But that is not the reason, but in a way you brought up something very important. So the most effective refrigeration should suck the most amount of heat from the refrigerated space. And that is dependent on what he is talking about. If a refrigerant has a high delta H of vaporization, enthalpy of vaporization, that is a good refrigerant. That will suck the most amount of heat from the refrigerator. Correct? You're thinking correctly. So that is one of the parameters you have to look for in a refrigeration when you select a refrigerant. Its enthalpy of phase transition should be very, very, very high. Only then it will act as a very, very, very good heat sink. And it should not be lost. There should not be material loss or heat losses. Third thing, the thermal conductivity from the refrigerated space to that material should be supposedly very good. Otherwise the heat will not transfer and heat will not get sucked in. So we usually look for these, and reversibility. You should be able to use it million times. So it should have the same enthalpy of vaporization how many ever times. So then the material's behavior should not change. And the entire refrigerant should come back as a liquid. Even if there is a little bit of vapor, the delta H will change. Correct? Got it? The whole liquid has to come back as a liquid here. Even if you have a little bit of vapor, gone. The heat sink efficiency will go down. That's the science of sucking heat out. You have to have a high drawing power. Anything else that needs to be looked at in refrigeration to make it a very good refrigerant?
enthalpy of vaporization here should be very high. The heat transfer between the refrigerated space and the material should be very good. There should not be heat losses anywhere here. It should be very good and insulated and directed right into your material. Anything else? One more thing, this should be very good. The work that you are doing to convert that entire vapor to liquid should be good. Got it? If you slack on this, what will happen? This will decrease. All the vapor will not get converted to liquid. Then you will have trouble again, next cycle. So you have to put the correct amount of work. No, there is no pressure in solid at all. That's the beauty of solid. We don't worry about pressure in solid. The concept of pressure slowly goes away in solid. It's a solid. That's the beauty of working with a solid. The good thing of not having vapor is we don't worry about pressure. So there, when the solid material becomes liquid, for me to convert it back to solid, I don't need to compress it. What would I do? I just cool it off. I will phase transition back again. Are you comfortable with the locations now? In this case, the arrow is going like this, bottom to top. In the other way, heat from the arrow says top to bottom. Careful, it's opposite, reverse. So what is Clochier's statement? He says that if you don't do work, QL will simply keep getting rejected as QL. So there is nothing, it's not a cyclic process. There is no gradient there, got it? So it will just remain as such. So you cannot remove heat there. You cannot remove heat. Wherever you have a cold junction, you should have a hot junction. It's like wherever you have a cathode, you should have a anode. Otherwise the process will not happen. Wherever you have a mass loss, next to it there should be a mass gain. Wherever there is a plus charge, next to it there should be a minus charge. Otherwise it's not natural. So where is the entropy increase coming from? Right here. So this process is spontaneous because heat is being rejected to the surrounding. Because here you will say the entropy is decreasing because you are doing work, agreed. But after you do work and it condenses, the heat is being rejected to the surrounding. So the overall entropy is still increasing. That is why if this QH did not happen, process won't happen. Yes? Process will not happen. If QH is not rejected back and the entropy of the surroundings does not increase, the process will not happen. Because here in the refrigerated space, when you suck the heat in, what happened to the entropy? Of the refrigerated space, what happened? Entropy decreased. Of the material, what happened? Entropy increased because the liquid became vapor. But then what you did here? You again reduce the entropy. So that won't work. It might negate each other out, but still the overall entropy has to increase. Where does it increase? Back out here. So heat got to come out. Entropy has to increase. So they don't say efficiency for refrigeration, they say coefficient of performance, COP. Again, output by input. What is your input? No, first you tell me what's your output in a refrigeration. Because he nicely said it should have a high enthalpy of vaporization, high enthalpy of melting. So what is your output that you require? I have to remove the maximum amount of heat from a refrigerated space. That is your output. What is it? Q? QL, where are you removing? Here, bottom. Can you write COP, coefficient of performance? Output by input. What is the output? QL. For that to happen, you have to do work. What is the input? Work. You are compressing. Work. What is the input? Just like your heat engine, what is the work? QH minus QL. If you compress it really well only, it will condense and give out the heat. Correct? If you do compression really well, only then you will get a high QH, which means you are ready to again have the material as a liquid. And it's back again, and it will suck heat again, and then again go back, you do work, and put it back as a liquid again, and back again and back again. So what is the work done? QH minus QL, write it. Write it. Obviously you know what the follow-up question is. How do you make the coefficient of performance very high? That you tell me. Just like a heat engine. You said I can make a heat engine to be very efficient if I decrease the heat that is being rejected. If I decrease the heat that's being rejected, QL, then you make the heat engine to be very efficient. Yes? Correct? How do you make COP very high? Huh? Okay, QL large. That won't happen by magic. QL is sort of not independent here, correct? Like there is nothing magical that it will go and take the heat in like that. That's what I said. That's why you have to think, because once again, you have to do work to make that magic happen. Yeah. So hold on, you want to increase? Okay, so obviously you have to increase the work done. So what you will increase? Only QH? If I increase only QH, then you will do lot of work. Your COP will go down. No, your thought process is correct. If I increase the QH and reject lot of heat without worrying about QL, then you will do a lot of work in the denominator. That COP is not going to be high. How do you reduce the work? How do you do this? Between what and what? Then if you have that, if the gradient decreases, then the process will come to a halt. That's the whole point. If you don't do work and you don't give a gradient of QH, process will come to a halt. If it's only QL and QL, it will stop. That will not work. If you don't input work, if you make work zero, that's the whole point. Clausius statement is if you make the work zero, QL is simply QL. Vapor will not again become liquid. Process stops. Got it? Get it? If you make work zero, there is no change back again. The vapor will not become liquid again. Where is the free lunch? Who is then now going to make it into, what will you do? It's over. Process will stop. If you do not compress, the process stops. Yes?
one time the vapor will become, one time the liquid will become vapor and then it will stop. That is all. So it's good to say make the work less, but if you make the work zero, you're done with the process. There is no refrigeration. So how do you make COP practically high? Yeah, one more time. Okay. Okay. So you want me to do less work again. If I do the less work, the gradient will decrease. How do you get high COPs? Something he mentioned a little bit. You keep both high, QL high and QH high. You have to keep both high. No? If I have a high QL and a high QH material, will my COP be high? Look this. Possible? But then why I need to do work? From your abstract fraction here, if I keep QL high and QH high, COP will increase, correct? So then you also know that if I have high QL and high QH, the amount of compression that I need to do is less. How do you explain this? I have a high QL and I have a high QH. So which also means that the work that is required by the compressor is less. But you still have a high gradient, but the work that you need to do is less. So the heat taking and the heat rejection both are very high. The heat that's taken in and the heat that's rejected out at the hot location is very, very high. Both are very high. So you don't have to do that much work. Does it make sense? Gradient will be but the temperatures will be different, correct? Yeah. Temperatures will be different. The amount of heat will be the same. Temperatures will be, or the temperatures will also become same. If I have high QL and high QH, will the temperatures become the same? Heat engine is easy. This is not very straightforward. Think about it. Come next class and I will start from this point only. How do you get a high COP in a refrigerant? Enjoy your Atmos. I think it's your first time Atmos. Yeah, there's a lot of things. Catch you guys. Have fun.